everyone. Thank you for coming. It's nice to see so many people on a sunny evening being interested in differential geometry. Today we will do two things. The first part will be still about curves in 3 dimensions, where we talk a little bit more about the curvature and the torsion, and especially look at how much information the curvature and the torsion together have about our curves. So that will be the first part, and then in the second part we actually start to talk about surfaces in R3. So the title of the whole lecture was curves and surfaces, and then we will now turn actually already towards like an initial study of some surfaces. But okay, let's start with some easy stuff, or relatively easy stuff about curves first. So last time we have seen that we, like once we have a curve in 3 dimensions, then we can define this frame, the Frenier frame, which was T and B, the tangent, the normal, and the binormal. And from that data, we could define the curvature and the torsion. And that's quite well-defined definition of the torsion. It's like something that the greatest formula was you take the time derivative of the normal vector, and then it's the torsion is the part that is in the direction of B. But this formula doesn't really tell you too much about what is that what is the torsion of a curve. Like for example, from that formula it might be not totally clear what is the torsion of a curve like this. So we would like to get a better geometric understanding of what the torsion is, and for that we use something similar to the curvature, where we also did some kind of Taylor expansion of the curve, and then the curvature was related to the second derivative. So let's try something like that again, and see if the torsion pops out there. So Taylor expand the unit speed curve C, and say we do that around some given time, and for simplicity we just take t equals to be 0. So then we all know how to Taylor expand. That means that we have some linear term related to the first derivative, and we have the second term which is related to a second derivative, and then keeps going on. And now we use the formulas that we had for the second derivative in terms of the Frenier frame. So for example, what we can use is that the second derivative is the same thing as the curvature at related to 0 and a normal related to 0. So that's just the definition essentially of the curvature and the normal. And then for the third derivative, we do something similar, which we can of course think about as t equals to 0 of the second derivative, which is just the curvature times the normal. That one is at 0. So we get 2 contributions. One of them is coming from the curvature derivative, another one from the normal derivative. And then for the normal derivatives part, we can again use the time derivative equals to something that comes from the Frenier equation. So if you use these equations, what you end up with is form minus the curvature 0 squared times here. So that's just like using the Friendly's error. And now we plug in these equations that we have, combined also, of course, we should write this on the top, that C0 is nothing out than just the tangent vector at 0. So we plug in all of these free data that we have in our first approximation, and then reorder terms to have like something that is in t direction, something in n direction. So we combine these two t's, and then something in b direction. If you plug this in, get something of the form. So we just recollected these terms that we got. And now let's drop all the terms that are, like, only take the leading order terms in each of these directions. So we're only interested in like the leading order in t that's happening in t, n, and b direction. So what we can do is we essentially can ignore these higher order terms. So this one goes, and this one goes, because it like gives you in the t and the n direction just some correction. So what we get is in total the following Taylor expansion, where we have so that's the final answer that we get. So now let's look at like the geometric interpretation of all of these terms that we have. The first one, maybe perhaps the simplest one, is that this one is linear motion in the tangent direction. So that shouldn't come as a big surprise, because the tangent is essentially giving you the linear direction, and then you say like, okay, in first order approximation, what I'm doing is like going in this direction. So that's like all what is like the geometric meaning of this one. So that's pretty unexciting. A little bit more exciting about something that we essentially have already seen is that the second order contribution here, so this one, or maybe put everything together. This one, so up to the second order, what we get is a parabolic motion in the Tn plane. And of course we see that one is like completely controlled essentially by the curvature. So this one is picture here, what you should have in mind is essentially that we have a certain direction with n and t, and then our curve in approximation looks maybe like something like this. So this is our curve, and let's say for kappa is 0 equals to bigger than 0. So you have kind of like a parabolic motion in t, and how much that parabolic is like open is given by the curvature. So something like this is what you should have in mind. And now, like this part here, we see there's the torsion in there, and it's something that is like in the b direction. So that's motion that is in b direction, which is to say that it's orthogonal to this Tn plane. And this motion is like, first of all, it's cubic, and it's completely controlled by the torsion. And the picture here would be something like this with tau is bigger than 0. Might look like something like this, where we have the b direction here, and this one is the Tn direction. The plane, and then you go out of the plane, and how much you get out of the plane is described completely by the torsion at that point. It's like essentially saying like how much this Tn plane is changing as you move on with the time. Do you have a question or? So that gives you hopefully some geometric interpretation. It's like the curvature essentially tells you in second order how much you're like curved. So how much is like in the Tn plane how much you're bending there, and the torsion tells you how much you're getting out of this nt plane as time goes on. But it's like something you can imagine as like a third order correction to that. So in some way we have seen that like the curvature and the torsion are very important to describe the local behavior of the curve, right? Like if you know the curvature and the torsion, then you know like locally around the point, like the third order, you know what's going on. So that raises the question, how much information is actually encoded in the curvature and in the torsion? It's like, can you reconstruct the curve in some ways? And to give you some idea of like how strong certain assumptions on the torsion and then the curvature can be, I want to give you like small little proposition. We start with a unit speed curve, as we have seen so often, and assume that it has curvature always stricter than 0. And then we have the following result. Then C is taking values in a plane. So essentially there's certain plane, and then in that plane the curve is moving, if and only if what do you think I should put here? Like, you have like a curve that moves in the somehow like in 3 dimensions, and you find a plane so that this curve is actually contained in that. So it's like something like this, where it's moving in a certain plane. What do you think would be what kind of geometric data is maybe controlling that? Yeah, so it's the torsion. Huh? So, like assuming that like it's already in like in a certain Tn plane, like the motion happening in a Tn plane, then we know that the third order there should be no contribution, right? So what needs to vanish here is the tau. Otherwise we get some third order contribution and we get out of that plane automatically. So the natural guess is that this one holds true if and only if tau is equals to 0. One direction is very easy, and I let that for you as like a small homework exercise, or you can think about that one. So if you have a curve that is taking values in a certain plane, then you just like describe that curve and calculate its torsion, and you see that it's 0. Or there's also a slightly more intelligent way to do that, but I leave that as the exercise for you. A bit more interesting, but also not very much hard, is that assuming that we have tau equals to 0, then we know from the Fourier equation that the time derivative of the binomial vector has to be 0. So that's just comes from the equations. So it's constant. So we have b of t equals to some constant. That's the b0. So that's b0 is a fixed vector. And the claim would be that C is now in the plane that is orthogonal to that vector. So that would be then really like that would be the Tn plane, right? So how do we prove that? Is that we define like in some way like a test function which takes the difference between the curve to some original point, and then take the dot product with b, b0, or with b itself. And then we take the time derivative of this one at an arbitrary point t. So this one is constant, this one is constant, so the only thing that we get is that the c of t times b0. B0 is nothing else than b of t. This one is nothing else than t. This one is t times b. And then we can use the equation that this one is related to the torsion, but our torsion was 0 by assumption. So what we get is that this function is actually 0. So f is a constant function because its time derivative vanishes. So in particular, we have that f of t equals to f of 0 for all times, but at f of 0, this term vanishes, so we are finished in some, because then the constant, like the function is always 0, and that means that the curve, or at least this expression, is orthogonal to this one. So that the motion is happening completely in this plane orthogonal to B. So it's again one of these tricks that you see, like it's quite useful whenever you have to do something with curves, is you look at some functions and then you take the derivative of that function, and you can handle that usually with some of these error equations in order to say that like a certain expression is like 0 and then constant in time, and then you can like use that effect actually what you want is that it's constant in, or like 0. So that's like usually the idea of like take the derivative, say something about the derivative to get something that you would actually want to conclude. Okay, so that gives you already some feeling that if you, for example, say that tau has to be 0, you get quite a lot of information about the curve, that it has to be in a plane. So it's like relatively rigid information that is giving you by just like knowing that the torsion vanishes. And the next theorem actually is even stronger. And so the question that theorem answers is like, how much information is contained in the curvature and the torsion? And I would like to do a little bit of an experiment, namely develop the assumptions that we have to put in that theorem with you together while going through the proof. So I will write like a first guess of what it might look like, this theorem, and then at some point we realize, oh, we have to put some additions and some further assumptions in there. So let's see what kind of assumptions we have to make. So first of all, let's say we have two, say, differentiable functions. Say they're defined on some closed interval with values in R. And then probably there's like a few more information that we need to give, but that would be the starting point. And our conclusion would, that we want is that then there exists a unique unit speed curve, which is defined on the same interval, that has exactly this kappa, curvature kappa, and torsion tau. So that's the form of theorem that we would like to discuss. Is like I give you two functions and ask you, can you find like a curve so that like these ones are the curvature and the torsion, and not like just like find one, but like we also would like to have that to be a unique curve, so that it's like completely characterized. So that will be like what we try to do. So it's like the So the first problem, or like if you think about this question would be, okay, how do I approach it? Would be, okay, the only thing that I know are essentially the Frenier-Zero equations. I would like to use them in some way. But then we had like troubles defining what is the Frenier-Zero frame at the point where the curvature was 0, because then essentially it's a straight line, and then it's no longer clear what you should take as like the normal direction. So in order to make sense, or like to have any meaningful way to approach that question, what we have to restrict ourselves is to a function where the curvature is already non-zero. So if it would be completely 0, then we would kind of be able to integrate it, but if it's like only 0 at some points, we already have some troubles, because I don't have any ideas what happens at these points. I would like to define the normal direction and so on, but like we had troubles doing that at like points with curvature 0. So let's restrict as a first assumption to completely positive curvature, and handle that case only. So now the second step will be, let's look at like what is usually the easy part, is namely that you say like something is uniquely characterized by certain properties. So that's usually easier than trying to prove some existence. So let's start with this. So we have two curves. Suppose we have two curves. Let's call one of them C and the other one has a bar. With the same curvature, which is given by kappa, and the same torsion, which is given by tau. So we somehow need to, like on what we want to prove, an ideal case is that like C equals to the other curve, so that like both curves are actually equal. So how would you do that is by, we need to somehow use the fact that it's kappa and torsion are given. And the only way that we can do that would be by looking at the Frenier-Zero equations and then conclude something about the Frenier-Zero frame, and then from that conclude something about these curves. So a natural guess is that we look at again a function. In this case, it's 1/2 of the absolute value where we have where we compare the tangent of both of these curves at the normal. And then at and so we define that as a function which depends on t. And if the curves would be the same, then t would be the same thing as like t bar. So in that case, f would be a 0 function. So we try again our trick that we had before, where we take the derivative of f, conclude that that one is actually 0, and then conclude from this that actually the t's have to be the same and the n has to be the same. So let's calculate the time derivative. And I will not do that too much, but what happens, for example, here is that we get expressions of that form. And so on for the b term. And what we do now is like we know what t prime is, like the time derivative by the Frenier equation. So we plug them in and like calculate what happens, and then you see that, for example, these mixed terms, like these terms vanishes because like t is has constant norm 1, and then you have certain mixed terms, like for example, here we have from the first term, give minus kappa n and then time t bar. So something like this. But on the same hand, here on this part we have n times, and then we get the term with a minus n bar prime. And if you write this one out, then we get here actually the same expression, but this time with a plus sign. And of course you get like a second term here. And similarly here you get like quite a lot more terms. So what happens actually if you calculate all of that with the Frenier equations is that all of these terms then cancel. So you have a certain term here that is cancelled by this, and then here you have like 3 more equations, and these ones are cancelled then by them. So what you see is that if you do the calculation at home, then you can convince yourself that all terms vanish. So what you get at the end is that the derivative is 0. So what we would like to conclude is that C equals to the C bar, which means that T equals to T bar. So what we calculate so far is that f of t is constant. So in particular, f of t equals the same thing as f of 0. But f of 0 is just like the difference between t and t bar at the point 0. So we need to somehow say that these ones are 0. So we have to fix that one. But there's no reason a priori that this one is the case, right? Like no of our assumption has like anything to do there. So that's why we have to actually put that one in our assumptions. So given these functions and certain vectors, and then we say that these ones have curvature and torsion, and when you separate frame at t equals to 0 given by these three vectors. So we have to give 3 vectors in order to like fix the Frenier frame at 0. Because if you do that, then like at 0, the t and the t bar are the same. Because by definition now they have the same Frenier frame at 0. So what we get now is that this part is 0 by our assumption that I just added. And because this one is 0, what we conclude is that each of these terms which are positive has to be 0. So we conclude that t equals to a t bar for all times. And similarly, n equals n bar and b equals b bar. Okay, so now we are already quite far because we saw that the curves don't have to be necessarily equal, but at least they have like the same frame for all times. But of course, this expression here says also something, right? Because this one is nothing else than ddt of c of t, and this one is just the time derivative of the other curve. So both of these curves have the same time derivative. So what we conclude from this is that C of t equals to C bar of t plus some constant. So that's a constant vector, and that's of course, if you compare, like say we take t equals to 0, then the constant is exactly the difference between these 2 points. So what we have to say also, in addition to fixing the Frenier-Serre frame at 0, we have to conclude that both of these curves have to start at the same point. Otherwise, they might start at different points, but then have otherwise the same Frenier-Serre frame, which makes also sense, right? If you think about, if you have 2 curves, the blue one and the green one, and both of them move like parallel to each other, then of course they have the same frame, because like the curvature and the torsion looks the same, but they start at different points. So they would be not the same, but they would be same up to the translation. So we also have to fix the starting point. So let's say we fix some point in our free. Then the frame would be the same thing, and now I'm running out of space, such that the curve starts at this point we have. So in that case, this constant would be 0, and the curves are indeed the same. So I hope I didn't confuse you too much with like putting like the assumptions later in, but sometimes it's like that's how you think about the mathematical theorem, is that you start very optimistic and say, let's try to prove something that I would like to prove, namely that 2 curves are equal if they have the same curvature and torsion, and then you realize, oh wait a second, like sometimes certain things are not behaved well, and like I need like further assumptions and put like certain conditions in there. And what we saw is that the type of information that we have to put in is that the frame at 0 has to be fixed and the starting point has to be fixed. Then at least the curvature and the torsion uniquely define the curve. So that's already quite nice. So now we have to do the opposite of, let's start with all of that data. Let's find a curve and prove the existence of the curve. The proof of that fact is very similar of the idea of using the uniqueness, where we have first said something about the Frenier-Serre frame, and then from that concluded something about the curve. And the same way we use a kind of the strategy here for the existence, where we say we first find the Frenier-Serre frame of the curve, and then integrate that one to get the curve back. So we first, as a first step, we get the Frenier-Serre frame. And then the second step is like the curve. So recall that we can the Frenier-Serre equations that we had before in the form that ddt of t, n, and b equals to a certain matrix times t of t. in that equation, this equation we got if T, N, and B would be the Fourier frame of the curve. So we don't know if that, if that's the case already, but we know that this matrix that we have here makes sense based on the data that we have, right? We have like kappa and tau, so we can define this matrix. So we could take the perspective and say, okay, we don't know T, N, and B as this curve of vectors, but we know that they have to satisfy this equation. So that's the perspective that we take, that this equation defines T and B, and for that we also need to know that T of 0 equals to T0. That was the assumption that we added. So this one is now an equation of a matrix, linear matrix equation for T, N, and B with given initial conditions. And I hope you had that in your ordinary differential equations course, that if you have a system like this, where the matrix is given and time dependent, then you always can find a actually unique solution of that equation. So that's like a standard theorem in ordinary differential equations. Tells you there exists a unique solution, which is of these equations. So again, the logic here is we have kappa and tau, so we define that equation and then define T, N, and B as the solution of these equations. What we have not shown yet is that these ones are an orthogonal frame for all times and that there's a curve for that. That will be the second part. But we have at least T, N, and B by this standard theorem from ODEs. So the next step is that we have to show that these T, N, and B that we just defined is orthonormal. And for this, using these equations that we just had, so we know that these ones are solutions. Using these equations, we can calculate what, for example, ddt of t times n is. And you get a certain formula which would be so you calculated this kind of term. So now you do this kind of calculation using exactly these equations to calculate all kinds of vector products or dot products. So we calculate T with B, get some expression, and so on. I think you get the idea of T and T. And essentially O NB, NN, and BB. So you do that for all kinds of dot products of all combinations. And what you end up with like is an equation which is like, again, very similar of the form that you have certain constants and then these D dot products that you calculate will come up again here on that other side. So you can think of that again as like a really huge vector that you take the time derivative of equals to a linear matrix times the same kind of dot products, which you then reorder. So it's like exactly the same kind of form like here, except now that we have dot products here and dot products there, and this matrix looks maybe a little bit different and more complicated. But it's exactly the same kind of form as over there. So we apply the same theorem from ordinary differential equations and say that these ones have like only have like a unique solutions to that. ODE theorem says that these kinds of equations have like a unique solution. If you fix the boundary term, so that's like, or like something that we have to fix. Namely, we have to not only say that these are arbitrary vectors, but of course we want them to be orthonormal at that initial point already. So here we have to add, of course, that these three vectors that we put in there are orthonormal. And under this assumption, then at t equals to 0, all of these terms vanish. And we can check easily that t equals to n equals to t times b equals to n times b equals to 0, and t times t equals n times n equals times b times b equals 1. And you can check that if you make this assumption, then these equations are satisfied.